Lesson 1-6, Representing Acceleration with Equations, Part 1. Let's, for this lesson, assume that t0 is 0, that we're starting the clock at time 0. So change in time is just going to be the final time. We're also going to assume that acceleration is constant. So our average velocity is the change in position over change in time, which becomes df, which we're just going to call d, minus do over t. Multiply both sides by t and add the initial position. You get that. Average velocity is also adding the initial and final and dividing by 2, which we could substitute in for the v average velocity and get that. Acceleration was change in velocity over time. So again, our final velocity we're just going to call v. If I multiply both sides by t, and then I add the v0, you have v equals at plus v0. All right, so if I take that equation and I add another v0 to both sides, then I divide both sides by 2. This is the average velocity. But we already had this formula from before. So if I take this and fill it in for my average velocity, and then distribute the t, you get 1/2 at squared plus v0t plus d0. Or we can take the v equals at plus v0. We could solve it for t. And we also have the average velocity. So I put it into the position equals average velocity times t plus d0. Substitute both those in, you end up with that. Multiply, including foiling there, and subtracting the z0, you end up with that. Then multiplying both sides by 2a, and adding the v0 squared, you end up with that one. So in summary, we have 5 equations. These 5 equations can solve most kinematics problems. These two usually work together, so it's more like we have 4-ish, and each of them is missing something. So this one has no acceleration, this one has no position, this one has no final velocity, this one has no time. Otherwise, our variables are d, d0, v, v0, a, and t. So you pick the formula that you need to use based on the letters you have. So, problem solving. How do we solve a kinematics problem? Start by examining the situation to determine which physical principles are involved. That might include drawing of pictures. Pictures are good. List your knowns. Identify the unknowns, what you're looking for. And then you find an equation or set of equations that can help you solve the problem. Substitute the knowns along with their units into the appropriate equation and solve. Then lastly, check the answer to see if it is reasonable, if it makes sense. If you have that the person is walking 500 meters per second, you probably did something wrong. A plane starting from rest accelerates to 40 meters per second in 10 seconds. How far did the plane travel during this time? Well, the rest means that our velocity is 0. In fact, though, but we start from rest, so that means our initial velocity is 0. So we're going to make a list of everything we know. Then we have 40 meters per second. That would be the final velocity. 10 seconds would be time. How far did the plane travel during this time? So we're looking for our displacement. Let's make the assumption, and we are assuming this, that our initial position is 0. So it says we accelerates, but they never told us the acceleration. So we're going to have to solve this without the acceleration. So we don't have the A. So maybe we could use the D equals average velocity plus D0. But I don't know my average velocity. Well, average velocity is V0 plus V over 2. So that would be 0 plus 40 meters per second over 2, which would be 20 meters per second. All right, so D is my average velocity. Time is 10 seconds. Notice the units will cancel out, leaving meters, plus the initial position, which is 0. So it looks like my distance is 200 meters, which is reasonable for a small plane. To avoid an accident, a car decelerates at 0.5 meters per second squared for 3 seconds and covers 15 meters of road. What was the car's initial velocity? Well, let's see. We know we decelerate at 0.5. So decelerating means we're going to slow down. So our acceleration would be negative 0.50 meters per second squared because it says it decelerates. Our time is 3.0 seconds. Our displacement is 15 meters. Let's assume then that we start at 0 meters. And we want the initial velocity. So we need a formula that has those 5 things. So how about the D equals 1/2 A t squared plus V0 t plus D0. That has all those. So D is 15. A is negative 0.50 meters per second squared. Time is 3.0 seconds. V0 is what we're looking for. Time is 3.0 seconds. And D0 is 0. Let's do some simplifying. So the 1/2 times negative 0.5 times 3 squared is negative 2.25 meters. The second squared's canceled. So I'd probably add the 2.25 meters to give me 17.25 meters. And then divide by the 3.0 seconds. When I do that, notice the units become meters per second. We end up with 5.75 meters per second. So that's how fast the car was going before the accident. Let's try another. A cheetah is walking at 1.0 meters per second when it sees a zebra 25 meters away. What acceleration would be required to reach 20 meters per second in that distance? Well, we're walking at that, so when it sees it, so that's the beginning, so that would be an initial velocity. And then we have a displacement. Since that's just our total displacement, we would say that we're probably starting at 0 meters. We're going to accelerate until we reach that speed, so that would be our final speed, or final velocity. And we're looking for what acceleration? So we don't have time here, so I need to pick one of the formulas that doesn't have time. So that's probably the v squared equals v0 squared plus 2a d minus d0. Fill in what we know. Oh, we're starting at 1.0 meters per second. Looking for A. Distance is 25 meters. Let's do the squaring. Be 400 meters squared per second squared. 1 meter squared per second squared. 2 times 25 would be 50 meters times A. Probably subtract the 1 meter squared per second squared to get 399 meters squared per second squared equals 50 meters times A. Divide by the 50 meters. So one of the meters cancels out, and I'm left with meters per second squared, and the number is 7.98 meters per second squared. So that is actually a very significant acceleration, but cheetahs are known for having great acceleration. The left ventricle of the heart accelerates blood from rest to a velocity of 26 centimeters per second. A, if the displacement of the blood during the acceleration is 2 centimeters, determine its acceleration in centimeters per second squared. So we're going to leave everything in centimeters here. We're starting from rest, so that tells us the initial velocity is 0. And we're going to that velocity, so that would be our final velocity, 26 centimeters per second. We're told the displacement is 2. So displacement is our total change in position. So that means our initial position would be assumed to be 0. And we're looking for the acceleration. So we need a formula that has those 5 variables without time. So that'd be v squared equals v0 squared plus 2a d minus do. Fill in the things you know. (26 squared is 676 centimeters squared per second squared. That would equal 4.0 centimeters times A. Divide by the 4 centimeters and you get 169 centimeters per second squared for your acceleration. Part B. How much time does the blood take to reach its final velocity? Well, we still know that we started at rest and that the final velocity was 26 and that our displacement was 2. So this time, instead of looking for A, let's look for T. Well, I could use this velocity displacement is average velocity times time plus the initial displacement. But I don't know the average velocity. So I could find the average velocity. Our initial velocity was 0. Final velocity was 26. Divided by 2 gives me 13 centimeters per second. So our final position was 2 centimeters. Average velocity was 13 centimeters per second times time. The initial position was 0. So really I just have to do 2 divided by 13, which gets me a time of 0.15 seconds.